Welcome to Space News from the Electric Universe, brought to you by the Thunderbolts Project at thunderbolts.info. In a recent Space News episode, we reported on two 2016 scientific studies that each serve potentially fatal blows to the hypothesis of dark matter. The first of these studies, reported in September of last year, found that the acceleration in the rotation curves of both spiral and irregular galaxies could be explained by visible mass alone, with no dark matter necessary. Professor of Physics and Astronomy David Merritt says of the findings, galaxy rotation curves have traditionally been explained via an ad hoc hypothesis that galaxies are surrounded by dark matter. The relation discovered by McGaugh et al. Is a serious and possibly fatal challenge to this hypothesis, since it shows that rotation curves are precisely determined by the distribution of the normal matter alone. Nothing in the standard cosmological model predicts this, and it is almost impossible to imagine how that model could be modified to explain it, without discarding the dark matter hypothesis completely. Another study reported in December presented a statistical analysis of mini-spiral galaxies and found a so-called unexpected interaction between dark matter and ordinary matter. A co-author of the study states, most dark matter, according to the most credible hypotheses, would be non-baryonic or WIMP. It would not interact with ordinary matter except through gravitational force. Our observations, however, disagree with this notion. In this episode, physicist Eugene Bagashov analyzes additional recent studies that raise even further doubt of the dark matter hypothesis, and he explores the growing scientific case for dark matter alternatives.
Following the recent Space News episode featuring astronomer Barry Setterfield, I'd like to briefly review some of the other recent studies regarding the dark matter hypothesis. First of all, there have been news from several experiments that theoretically could detect processes involving dark matter particles. For example, the team of researchers working with Fermi Space Telescope indicates that there are no signs of dark matter particle annihilation nor decay. These processes should take place if dark matter particles could interact not only gravitationally, but also perhaps through weak nuclear force. The gamma-ray flux measured by the Fermi telescope from low Earth orbit over the course of several years so far have not shown the evidence for any significant dark matter presence. Experiments on and below the surface of the Earth have also failed to detect any specific dark matter processes. There have been news from Panda X experiment in China. They've used 300 kilograms of liquid xenon to detect the collisions of its atoms with the supposedly present dark matter particles, and over the course of at least 66 days haven't detected any single event. At the same time, the article published by the team of experimenters claims that this laboratory at present is the most sensible to dark matter on Earth. Another similar experiment called LUX is also using liquid xenon, and it also have recently reported the complete absence of events of dark matter candidate detection. 20 months of observations from October 2014 to May 2016 have yielded 0 observed events. Third experiment using the same technique is Xenon 100. 477 days of data taking have not resulted in a detection of a single dark matter particle interaction. The Large Hadron Collider, which once was a big hope for finding lots of what is called new physics, have also not produced any new findings in the recent years. What it does now is basically refining the previous measurements with more and more statistics and putting more and more strict constraints on the theoretical physicist's proliferative imagination. Speaking of which, I would like to remember a story from the end of 2015 when there was a message from experimenters at LHC stating a possible detection of a 2-photon peak at the energy of around 750 giga-electron volts. This was quickly followed by literally hundreds of papers submitted by theoretical physicists, each stating his own hypothesis on what this peak might stand for. Some of the versions included possible dark matter connection. But perhaps the most embarrassing was the fact that this peak just disappeared a few months later after accumulating more data. It turned out to be just a statistical artifact. But the social phenomenon of this theoretical physicist rush have itself turned into the object of public and scientific attention, including some jokes and sarcastic publications. In the previous episode of Space News on Dark Matter, Barry Satterfield have already made the point that there is a more or less suitable mathematical alternative to the dark matter hypothesis, the modified Newtonian dynamics, or MOND for short. In the recent years, other theories have also appeared. Some of them are quite eclectic, trying to tie various physical concepts with gravitation. I think the most interesting of them is the so-called entropic or emergent gravity. It seems that a few people were developing it even earlier, but the most popular version of it nowadays is the one proposed by Eric Verlinde. In his paper published in 2010, he states that the amount of information associated with matter and its location could be measured in terms of entropy. Changes in this entropy when matter is displaced leads to an entropic force, which, as he shows later, takes the form of gravity. So its origin lies in the tendency of the system to maximize its entropy and is thus thermodynamic in nature and isn't actually a result of any fundamental force of nature. I'll remind that today 4 forces are considered to be fundamental, and that is electromagnetism, gravitation, weak and strong nuclear forces. In case of Verlinde's theory, the fundamental interaction that leads to emergence of gravity would most likely be electromagnetic. He also gives examples of other emergent forces such as osmosis and similar entropic forces in colloidal systems, where the fundamental interaction is clearly electromagnetic, since all the mechanical forces such as pressure or elasticity are electromagnetic in nature. Now I'll try to explain in simple terms how I interpret the basic idea of Verlinde's theory. Let us consider as an example the system of two-point masses A and B. We always might draw a sphere centered on one of those, for example A, with the radius equal to the distance from A to B. In this case, the mass B would lie on the sphere. Such a system might be treated in informational sense. That is, for example, the position of the body B with respect to A might encode some information. Let's say we divide the whole sphere in 100 sectors of the same area, and each sector would correspond to some number. Then the current position of a body B on the sphere would point at one of those numbers, thus giving us the according information. Let us now consider another case when the body B is slightly closer to the body A. Now we might repeat the same drawing procedure, but soon we would find that the number of sectors that we might divide the sphere in is actually less. If we try to keep the same area of sectors, it is obvious that we couldn't fit the same amount on a smaller sphere. So the amount of information that we might encode in this smaller system became less. Thermodynamically, this means that the entropy has increased, and the system now might provide less ordering. So the system with masses situated closer together is thermodynamically more stable, and it is in this direction that the evolution of the closed system would go, and there is an effective entropic force that arises to guide this evolution. It is possible to formally derive the according equations, and Verlinde does that in his paper. In my opinion, the idea is quite interesting, and at the very least deserves a careful and thorough analysis. However, there are some problems, and perhaps the weakest spot of this theory is its reliance, at least in mathematical terms, on the so-called holographic principle and ADS-CFT correspondence. Both of those are pretty specific theoretical conjectures and are highly speculative in nature. Anyway, what interests us here in the given context is that based on his own approach, Verlinde seemed to have succeeded in acquiring equations that are practically identical to Milgrom's Mond equations for large-scale gravitating systems such as galaxies. And more than that, in December of 2016, there appeared a publication that claimed incredibly accurate confirmation of Verlinde's predictions for the case of gravitational lensing. Of course, the very phenomenon of gravitational lensing is somewhat doubtful, though Verlinde's theory could actually shed more light on its nature. If gravitation is not even a fundamental force but some emergent effect, maybe this would also concern the propagation of electromagnetic waves. That way or another, the theory is there, and the publications that seem to suggest its practical value are starting to appear. So now, not only we don't register any dark matter particles, but we also have at least 3 alternatives to dark matter hypothesis itself. First one comes from plasma dynamics, the second one is MOND, and the third one is Verlinde's emergent gravity. In my opinion, it is a very good situation for science as such, and one should try to encourage the existing controversy, since it is the controversy that is the real life of science. This actually brings hope for the academia as a whole, with its dogmas of settled science, and possibly it could even serve as a sort of a pivotal point for the scientific revolutions in other areas in the coming years. With the current political situation in both the European Union and the United States, as well as the imminent stock market and banking system crisis, it is entirely possible that there would spark major scientific debates in the areas that only recently were considered to be totally settled. But as the scientific institutions would try to adapt to the new reality and shifted financial flows, the situation would become different. In my opinion, this provides a certain opportunity for many alternative schools of thought, including the electric universe paradigm.
For continuous updates on space news from the electric universe, stay tuned to thunderbolts.info. Most dark matter, according to the most credible hypotheses, would be non-baryonic or WIMP. It would not interact with ordinary matter except through gravitational force. Our observations, however, disagree with this notion. In this episode, physicist Eugene Bagashov analyzes additional recent studies that raise even further doubt of the dark matter studies that each serve potentially fatal blows to the hypothesis of dark matter. The first of these studies, reported in September of last year, found that the acceleration in the rotation curves of both spiral and irregular galaxies could be explained by visible mass alone, with no dark matter necessary. Professor of Physics and Astronomy David Merritt says of the findings, Welcome to Space News from the Electric Universe, brought to you by the Thunderbolts Project at thunderbolts.info. In a recent Space News episode, we reported on two 2016 scientific studies, and it is almost impossible to imagine how that model could be modified to explain it, without discarding the dark matter hypothesis completely. Another study reported in December presented a statistical analysis of mini-spiral galaxies and found a so-called unexpected interaction between dark matter and ordinary matter. A co-author of the study states, galaxy rotation curves have traditionally been explained via an ad hoc hypothesis that galaxies are surrounded by dark matter. The relation discovered by McGaw et al. Is a serious and possibly fatal challenge to this hypothesis, since it shows that rotation curves are precisely determined by the distribution of the normal matter alone. Nothing in the standard cosmological model predicts